Hello, you absolute legends. The third and final point on a weak acid and strong base titration curve is when the moles of base equals the moles of acid. This is called the equivalence point. The equivalence point occurs in this tall vertical, very vertical part right here. The equivalence point is not always going to be at 7 pH. Okay? It might be a little low, might be a little above. But the equivalence point can be observed if you try to find the straightest, the most vertical portion of this very steep section right here. You can read the pH on here. At this equivalence point where all the moles, this is at the equivalence point. At the equivalence point, the moles of acid and the moles of strong base are equal to one another. It doesn't matter what they are, what the number is, we just know that they're equal to each other. When they're equal to each other, we say that all of the weak acid has been consumed by the base. If all of the weak acid has been consumed, what is dominating our perspective of the equation? When all of the weak acid does this job here, that means that every single one of those molecules is being converted into the conjugate base. The conjugate base. Conjugate bases increase pH by stealing protons. So we have in a weak acid strong base titration, this equivalence point is a pH greater than 7. How do you calculate exactly what that pH is going to be? We need to look at this equation, what this molecule is doing. Yeah, that's fine. This formula here is meant to represent the conjugate base taking available water molecule protons to form the acid and to form this base right here. This right here is changing the pH, making the pH be higher, increasing. We run a Rice table. When the moles of acid equals the moles of base, we run a Rice table of the conjugate base. The molarity of the conjugate base is whatever we started with in moles of acid. When we set up this experiment, you know how many moles of acid you put in there, and if all of it has been converted, then we know this concentration. I'm just going to put 0.1 in there as a placeholder. Liquid water, I don't care about it for Rice tables because it's not in the capital K expression. HA, don't know, zero molarity there. This is going to go down, this is going to go up, and this is going to go up. So far, this Rice table feels very similar. 0.1 minus 1 minus x. X, okay? This is our E line here, okay? These go in the denominator. This goes in the products here, and the numerator, because products are always on top. So we have a K expression that looks like this, X this K expression, taking our E line and plugging it into where those species are, this is a product. So I'm saying this X is representative of HA. This X is representative of OH minus. This denominator, we often drop this out. You have good physical reasons to do that mathematically, but we drop this out to 0 here. So we're left with an equation with only one unknown. Wait a minute. Two unknowns. We have x squared and this k here. This is not Ka. This is a base reaction. This is Kb. Kb is easy to calculate because of this relationship of acids and bases when they're in water. I have this kind of scrunched in here, but Ka times Kb will equal 10 to the negative 14th. You know, in water at 27 degrees Celsius, if we had a different temperature or a different liquid, this number would be different. But this is a relationship that's good for water. We will often know one of these. So you have two unknowns in this equation. If you know one, you can calculate the other, and if you know the other, calculate the other right there. If we know Kb, we can calculate these numbers here. Because we know this number, we know this is just x squared. We have this right here. Now if we solve for x, we will only be solving for the molarity or concentration of OH minus. X is the moles per liter of our base OH minus. It's also the same value of this one right here, but this is what we're looking at. This is the one we're focused on right here. OH is not pH. We're trying to find pH right here. We have a second relationship that POH plus pH equals 14. When you are at in a weak acid, strong base, equivalence point, run a rice table with some math magic that needs to be placed in here. We have a rice table of the conjugate base, and we solve this very similarly to point 1, except we have to keep in mind kind of things here. Ka times Kb equals 10 to the negative 14, and POH plus pH equals 14. And these are not a coincidence. They have specifically things to do with water here. I hope this helps. Thank you.